Hello everyone. In this video, I am going to talk about chapter 16, section 16.5. We talk about in our last video, our last section, we talk about our motions going to have translational motion, rotational motion, or a combination of translational rotational motion, right? So today we are going to look at some examples that's somewhat a combination of them, and we're going to perform a relative motion velocity analysis of point on the body. So looking at this rod AB going from the first position, initial position time t, going to the second position t plus dt, okay, at the second time. So apparently this is going to be a general plane motion. It's a combination of translational and rotational motion. So what we're going to do, since general plane motion is kind of complicated, right? We are going to break our motion into two parts. First, we're going to translate it and then we rotate, or we first rotate and then translate. But either way, we are breaking the translation and rotation separately. So from AB, going from instead of this is the initial and the final, right? We are going to add one additional position in the middle, which is the red one that I just drew over here. Going from the initial to this red one, which didn't really exist, but it's like an imaginary transition in the middle from the initial to the red one that I drew, it's pure translational motion. And then from the red one to the final, we're doing a rotational motion. Okay, so we're breaking that down into two steps. So starting looking at the triangle at the bottom, let me use a different color. Let's go with green. This triangle at the bottom, we see, looking at this triangle at the bottom, okay, just keep in mind it's the triangle at the bottom. We sort of see this triangle before when we talk about a relative motion. In there, you have d r b position vector b, and then you have position vector ra, and then in between them at the bottom of this triangle, this one right here is the relative position of b with respect to a, so rb slash a. So we can put this in this equation right here. Displacement due to translational or in rotation, the rb equals the ra plus the rb slash a. So it's equal to the translating plus the rotating. Okay. And then next one will be the velocity at B given as the RB over RT. We're taking the first derivative of this position vector with respect to time. That is going to give me the relationship, the A, the B, and the relative velocity of B with respect to A in an equation, right? So we've seen this before. The position equation, first derivative, that gives you the velocity equation. And then since the body is taken as rotating about A, so your VB slash A will be d RB slash A with derivative with respect to time. And then this gives me omega times RB slash A. Okay, so we are going to look at this equation a lot today. VB equals VA plus omega times RB slash A. We're using this relative velocity equation. Position A and B should generally be pointing on the body with no motion. Often these points are pin connected in linkage, so they are connected. And then point A on the link AB must be moving on a horizontal path, for example, whereas the B moves in a circular path. The direction of VA and VB are known since they're always tangent to the path of motion. I will show you in an example of what I mean. This diagram over here, what I want to show you is that, okay, we know that when the wheel is turning on your car, on your bicycle wheel, right? When it's turning, we always thought, the middle is going to be the center of rotation, will be the center of the wheel, the B. Normally that, right, before you studying this class. But I want to point it out to you that now in our dynamics class, at any instant, let me use a different color so that you can see this better. We always assume center of rotation is right here. In our dynamics class, in today, what I'm about to show you is that at any instant, so every single moment at that fraction of the second, your center of rotation will be right here, down where the contact point, where the wheel is in contact with the ground. That is that instant at that specific frag of a second, that contact moment will be where the wheel is rotating about. So up here, right, I'm rotating here. I'm rotating any point on that on the wheel is rotating about the point that is in contact with the ground. Okay, so if you are having a point right here, perpendicular to here, okay, it's rotating about that point. If you have a point over here, connecting that to the center of rotation, that location right there is going this way. So that's perpendicular. That's perpendicular. We'll probably see this diagram again in the near future, but just so you know. Okay, so let's keep going. Let me get this right. Let's keep going. So point B at the center of the wheel moves along a horizontal path. So the point B in the middle, the center of the wheel will be moving on a straight line horizontally if your floor is flat, right? So VB has a known direction parallel to the surface. So procedures, what do you do, right? The relative velocity equation can be applied using the scalar xy component equation or via a Cartesian vector analysis. Using the scalar analysis, we're going to establish the fixed xy coordinate directions and draw a kinematic diagram for the body. Then we're going to establish the magnitude and direction of the relative velocity vector VB slash A. We're going to write our equation VB equals VA plus VB slash A. In the kinematic diagram, represent the vectors graphically by showing their magnitude and directions underneath each term. We're going to write the scalar equation from the xy components of these graphical representations of the vector. We're going to solve for the unknowns. So for your vector analysis, once we establish the fixed xy coordinate direction and draw the kinematic diagram of the body, we're going to show the vector VA, VB, and then RB slash A and omega if the magnitude unknown and the sense of direction may be assumed. We're going to express the vector in Cartesian vector from the CVN and substitute them into this equation. VB equals VA plus omega times RB slash A. Evaluate the cross product and equate the respective the I and J component. So really it looks like what it's saying is that it looks like it's one equation here. Where my mouse go? Right here. It looks like it's one equation go over here, but it really they have the I and the J component. It really is two equations. I can separate this equation right here into the I equation and the J equation. If the solution yields a negative answer, the sense of direction of the vector is opposite to that assumed. Let's take a look at some examples. So I have this rod right here hanging against the wall. Rod A, on the A end is moving to the right 3 meters per second, and the B is moving down 30 degree angle theta. So we're looking for the velocity at that instant when that theta is 30 degree. We do know that velocity A is going to the right. So in other words, the direction of that A is purely to the right. And then the velocity B is coming straight down because it's hanging against the wall. It's leaning against the walls. That means the direction of the B is going to straight down. You only have the J component of that B. For your A, you only have the I component of that A because I'm going to the right. Putting into this equation, I have VB coming down, only J component, VA to the right, only I component. Okay, so this two. And then putting this the second part, omega RB slash A. Omega, we don't know. Omega is we don't know, so we leave that in there. Now, this term right here, RB slash A, if you figure, well, what exactly is that? So the definition is relative position of B with respect to A. What you're going to do if that confuses you is that you're going to assume from B, you're going to assume A is your origin. If the coordinate of that A is 0, 0, how would you write the coordinate of B? Coordinate of B right here, I am to the left of you. That means I have a negative X value. And I'm on top of you. That means I have a positive Y value. And then the rest of them, the actual, how much that is, will just be a sine, cosine 30 for the X value. I am negative, but I'm this much negative, which will be the 1.5, which is the hypotenuse, 1.5 times cosine 30. And then I'm going up, I am this much above on the Y, right? So that will be 1.5 times sine 30 Okay, so that's where that comes from, including the sign and the magnitude. So assuming so relative position of B with respect to A, assuming A is 0, 0, what would be the coordinate value of B? So that's how you put that together. And then overall, there you see a cross product. And then in here, in this equation, what you're going to do is you are going to separate the I and the J. So what it's saying is that, okay, I and J, because they're vectors, right? So I put all the J, this part, then this part together. That will give me this equation. Okay, let me use another color. And if I put, what's a good color? Let me use black. And if I put that one, which is I, and that I together, and then left hand side, there's no I. That's why you have a 0 here. Put all the I together, put all the J together. I'm solving for the value of omega and VB. Okay. So that's our first example. Example number 2. You notice that the piston for the B end is going to go up and down. Okay, over here, this is going to go, piston B is going to go up and down. That means if I'm looking at the velocity of that B, you only have the J component because the B can only go up and down. For that OA, it's rotating about 0.0. Okay, A can only go the this way, that way, rotating, right? And then so what are we looking for? We have OA with an angular velocity of 12 radians per second. We're looking for the velocity of piston B and the angular velocity of raw AB. Okay, again, we have our equation. We know that velocity A at that moment, since right now it's vertical, right? At that moment, VA is going to the left. At that moment, VA is going to the left. So I am going to do velocity. Remember, we say linear velocity is going to be the radius multiplied by the angular velocity, r omega. R is 0.3 meter, omega is 12 radians per second. And it's negative because at that moment I'm going to the left. That's where that comes from, okay? Negative 0.3 times 12i. Now, plug that into the equation VB equals VA plus omega AB cross RB slash A, right? This equation right here, we know that VB, back to our problem, we know that VB is only vertical, so you only have the J component. VA is only horizontal at that moment. It could be J component, but for that, at that instant, your VA is going to the left and it's negative, so you have that. And then keep going. Over here, you have our B slash A again. What do we do with the B slash A? Assuming your A is origin 0, 0. If I have 0, 0 over here, what is the coordinate of B? What's this one right here? And notice that it is to the right of me. So you have positive X value. Over here, this term is going to be positive. Okay, and then you have coming down, B is below A, so that's why you have negative value. And so positive I and negative J. How much is the value? So you're looking at this triangle using the sine and the cosine 30-degree. So your X value for the B is this much, right? So that would be 0.6 cosine 30. That's where that comes from on the magnitude, and it's positive because I'm to the right of you. And then the y value, it's actually given to us on the graph 0.3, but if it's not, you can use that 0.3 0.6 meter, and then this end, right, that will be 0.6 sine 30, but either way it should give you 0.3 because sine 30 is 1/2, right? And it's negative because B is below A. Putting that together, again, you are going to separate the X and the Y. Let's see, your, not X, Y, your I and the J, but it's the same thing. So your I is going to be that one. Ooh, let's try it again. Your I is going to be that one and that one. Left hand side, your I is 0. So that is 0 equals negative 3.6 plus 0.3 omega AB. And then your J component is going to be J there. You have J there. And so put that together. That will help me have a relationship between VB and omega AB. Two equations and two unknowns. I can solve for the omega AB and the VB. All right, next one, group problem. So I have rod AB rotating with an angular velocity of omega AB 60 radians per second. Velocity of the slider block C So the C goes up and down. So if we're looking for the velocity of C, you only have J component. So the theta over here, we're assuming when theta is 60 degree, when the side angle psi is 45 degree, what would be the velocity of the slider box C? Okay. So since link AB is rotating omega AB 60 radians per second, velocity at point B will be VB equals omega AB across RAB. At 60 degree, VB equals 60K cross this is zero point 0.3 sine 60i, zero point 0.3 cosine 60j. Put that together. And so basically what's saying is that, well, at A, right, at location from the link AB, I can use what's going on in link AB to help me figure out the linear velocity of B, linear velocity at point B. Okay, so because I know the angular velocity of AB. Okay, now with that no VB no, we can plug into this equation. We're looking at the rod BC, CVC, since it goes, so you put that into this equation. Now we go to the rod BC now. Your VC equals VB plus omega BC cross product cross RC plus C slash B, relative position of C with respect to B. So your negative VCJ, C goes up and down, right? Since at that moment it comes down, you have negative VCJ. And then over here, VB, we calculate it from the previous slide, and then you plug in the omega BC and RC slash B, right? Relative position of B with respect to, sorry, relative position of C with respect to B. So if the annotation is too much, right here, go back to the original diagram, however, to help you figure that out. So basically, you have a 45 degree relative position of C with respect to B. So in other words, if I assume a 0, 0 over here, what would be the coordinate of C? Apparently, it's to the left and coming down of where the B is. So that's why you have negative value on the X and negative value on the Y. And since this is a 45 degree, that would be negative 0.6, 600 millimeter converting to 0.6 meter, right? So that would be sine cosine 45, which is the same thing. And then putting that together, I am setting the I, separate the I component and the J component separately. We can calculate omega BC and the VC. Okay, so that's what I want to share with you in this video, students. Thank you for watching. Hope you find this helpful.